Okay, I think we're going to go ahead and get started here. And today we're going to look at the second half of the general senses and talk about proprioception and reflexes. So does anybody have any questions on anything? Okay, in that case, I'm going to go ahead and get into, here we go. Okay, oops, got carried away with myself there. Hang on one second. The last thing we talked about last week was adaption. Sensory receptors can adapt. Some can anyway. Some can adapt very quickly. Some don't ever adapt. We can adapt to pressure. We can adapt to touch. We can adapt to smell. We get used to odors very easily. After a while, we ignore the odor because our sensory receptors for olfaction are just overwhelmed with it, and we just ignore it. We get used to touch. We don't pay attention to the touch of clothing on our skin, for example, or shoes on our feet, or sandals on our feet, or whatever. We don't pay attention to that. We don't pay attention to pressure. If you're sitting in a chair for a long period of time, until you stop and actually think about it, you may not be paying attention at all to the pressure of the chair on your butt. We don't usually think about stuff like that. You're on a long trip in a car, for example, and you get out of the car and then you realize, oh, I'm stiff, I'm sore, my butt hurts, or my back hurts, or something like that, or my legs asleep. All because, but you weren't aware of it at the time, because we adapt. The stimulus of the pressure, it was still there, but we no longer respond to it. Now, some receptors, we don't ever adapt. Pain. We never adapt to pain. Pain is our warning signal that something's wrong, that we shouldn't be doing something, or that something is, hurting us. So pain, we don't adapt to it. We can get used to pain. We can get used to chronic pain. We know it's there, it hurts, but we live with it, but we never get used to it. We don't adapt to body position. We always need to know where our body parts are all the time. And we never adapt to the chemical makeup in our blood. Our blood, our pH is constantly changing. We become acidic. We basically respond to that instantly. We respond to the level of oxygen in our blood, or the level of iron in our blood. How much water do we have? How much salt do we have? Our kidneys are constantly adjusting for the makeup in our blood. So we're always monitoring concentrations. So we're never going to get used to, oh, well, we've been acidic all day, I'm just going to let it, I don't care. It doesn't work that way. We pay very close attention to the chemical makeup that we have. So those things never adapt. Those things never adapt. Pain and body position, as in proprioception, not just touch or pressure, but body position. Where is our position in space? That's proprioception. Don't ever adapt to that. And we definitely never adapt to pain. So what is proprioception? Proprioception is self-awareness of our position in space, in location. It is our awareness of movement, how rapidly we're moving. When we're running, we're walking, we're swimming, we're hiking, we're driving, we're bicycling, we're moving our arms and legs. We are aware of that movement. We may not be consciously aware of it, but we're definitely subconsciously aware of the movement. How rapidly are we moving forces around? Are we exceeding our ability to move our arms and legs? We monitor our position using proprioceptors. They are mechanoreceptors. They're neurons found in the muscles themselves. They're found in the tendons attached to the muscles, and they're found, excuse me, at the joints. And so not only do we respond to location, we respond to motion, velocity. How fast are we moving an arm or a leg? Are we doing something? Are we engaged in some activity that we're exceeding the ability of our arm or our leg to do what we're doing? Are we exceeding the limits of what that arm or leg can do? When we talk about loading, what kind of weight demands are we applying to that arm or to that leg or to that body part? So while we may not be consciously aware of any of this, we are definitely subconsciously aware of what's going on. The central nervous system is doing this for us. It gives us a comprehensive picture of where we are in space, what we're doing, and are we moving? Are we accelerating? We are, even when we're in a car, if our eyes are shut, hopefully we're not driving, but if we are in a car and the car is moving and our eyes are shut, we are still aware of acceleration and turns and position, because our central nervous system uses the sensors embedded in our muscles, as well as other sensors in our body to tell us what's going on. So now, proprioception is a constant monitoring process. We are always prepared to respond to any kind of disruption. We trip and we bring ourselves upright before we fall, or we trip and then we fall. We run into things or we don't. So we are always going to be trying to respond to any kind of disturbance. We have to monitor our posture all the time to stand upright. We have to work very hard to maintain balance. Believe it or not, while it seems like it's second nature to us, we have to constantly adjust muscles to maintain our balance. So we are doing this all the time. When we're walking on a rough surface, like going on a hike in the mountains, on a path or a trail we've never been on before, or we're walking across a steep slope or a wet field where it's slippery, walking on snow or ice, we have to constantly adjust our muscle response there. We have to be able to adapt to the irregular surfaces that we encounter, or the smooth surfaces. Maybe they're too smooth for us. We have to adapt to that too. So we're adjusting our muscles in how they respond to that kind of motion all the time. We use our proprioceptors telling us what our muscles are doing, what our joints are doing, what our arms and legs are doing, how fast we're doing it. All the time. Consider what happens when you trip or you slip you fling your arms out, you throw your head up and try and adjust. So to try and recover your balance, and you slip and slide, trying to move around, to hold that, to recover your balance. Because we still know what our balance is. We still know what is up. And we try very hard to get ourselves back in that position. We also use our proprioceptors to control our muscles so that we can turn on and turn off one set of antagonists. Because muscles work in pairs as an antagonist. Biceps against triceps, for example, quads against hamstrings. They are paired like that, and we can inhibit one side or the other when necessary. Okay, now consider this. Proprioceptors can respond very quickly to sudden changes. You're holding a bag, holding a plastic bag, and someone dumps a bunch of, I guess it looks like oranges or maybe yellow tomatoes. Let's just say they're oranges. You're holding a plastic bag and someone dumps 5 pounds of oranges in the bag. The first thing that immediately happens is that the extra 5 pounds of weight plus the force of gravity accelerating down there puts a pretty significant weight load on that bag and causes your arms to stretch, the muscles to stretch in your arms as your arms sink down because of the sudden weight gain. But then, because there's been a change in the muscles in their position and their contraction, the proprioceptors, the proprioceptors in your muscles called the muscle spindles will tell you to bring your arms back up. You have a reflex. You reflexively bring your arms back up to where you were holding the bag. You knew the original position. You were disturbed by the extra weight, but you brought the bag back up to its original location, despite the fact that there were 5 pounds of oranges there, and now you're contracting your biceps and or your triceps muscle to overcome that weight. So now there are 3 types of proprioceptors that we encounter. Muscle spindles. These are found in our skeletal muscle, right in the middle of our muscles. This is a muscle spindle. We have the Golgi tendon organs located where the muscle and the tendon come together. You know, the outer covering of the muscle, the excuse me, the epimysium layer that covers the entire muscle forms the tendon. That interface is where the Golgi tendon organs are located. And then the joint receptors, or the joint capsule receptors, are located in the synovial capsule. The synovial joint, that surrounds all of our flexible joints, all of the freely movable joints, the capsule that surrounds each of those joints, like in our fingers and our toes and our hands and our feet, arms and legs, shoulders, elbows, knees, all that stuff. There are mechanoreceptors embedded in the capsules that are stimulated when they're distorted. So this is a muscle spindle. Now the muscle spindle can measure a number of things here for us, including velocity. How fast are we moving the arm or leg? Are we driving a nail? Are we kicking a football? Are we throwing a baseball? Are we riding a bicycle? Any of these things. How rapidly are we moving the limb? And what kind of movement do we have? That we can measure with the change in the length of the muscles and how rapidly, it's the change in the length of the muscle and the rate of change. How rapidly the muscles change their shape, short and long, because all a muscle can do is contract. You can't do anything else. But we can detect how rapidly we are contracting or how slowly we're contracting. And we can tell where the arm is or the leg is and how fast it's moving. What kind of movement do we have and how rapidly is it moving? The Golgi tendon organ is located, you can see where the tendon is coming off of the muscle. We can see that the Golgi tendon organ is right at the point where the muscle and the tendons come together. They can tell us what kind of resistance the muscle is experiencing. How hard are we working? What are we trying to overcome? What forces are we trying to overcome? That's what the Golgi tendon organ does for us. And the joint kinesthetic receptor or joint receptor are found in the joint itself, in the capsule surrounding the joint. We can detect extreme changes rapidly in here. They can tell us when we are at the edge of causing some problems. We are at the threshold, not threshold like in muscle contractions and action potentials, but the threshold of pushing the edge of the joint too far. The extremes of the position before we cause damage. That's what the joint receptor warns us about. When we are at the extreme position, are we about to hyperextend our knee, for example, which we don't want to do. Okay, now, something else we might see with proprioception, and we do this all the time. This is called non-conscious proprioception. This is known as the righting reflex, where we try to find our horizon. Regardless of our body position, whether we're, regardless of our position in space, tilted, standing upright, seated, slouching, laying down, we always will try to line up our eyes with the horizon, wherever the horizon is, whatever the horizon is. What this does is this is how we have a baseline for balance, this righting reflex. We will always tilt our head into a position that's level with the horizon, no matter what position we're in. We see this right away with infants. When an infant who is crawling will crawl with their head raised, they do this to as when they gain control of the muscles of their neck. When an infant is learning to crawl before they walk, they will start raising their head up so they can see the horizon. They don't know it's the horizon, they just know it's level. And they're using that to stabilize their equilibrium. We do it too. So no matter what position we're in, we lean sideways, we're still going to tilt our head back so that we can be lined up with the horizon. The righting reflex. Our body leans to the left, we're going to be aware of it. The special sense for balance and equilibrium inside our inner ear is going to tell us that we're tilted to the left, but we don't want to be. We want to, even though we're tilted to the left, we want to be at least know what's up, which direction is up. And so we will move our head so that our eyes line up with the horizon. So even though we're tilted, or even though our body's tilted, we still know what direction is up. We still identify the horizon. This is known as the righting reflex. So we always know which side is up. Okay, so that is non-conscious proprioception, the ability to try and maintain our balance, to automatically find out what's level, what is up. So now we also have conscious proprioception. Conscious proprioception is directly communicated to the cerebellum. So that we're always aware. The cerebral hemispheres. The cerebral hemispheres, particularly the cerebral cortex, is where we as individuals are located. The cortex, the outer covering of the outer layer of the cerebral hemispheres, the two big structures of our brain. Everything about us is usually found in that outer layer there. We send information on our position there to tell us what's going on. So we're aware of our surroundings. we send non-conscious communication, like the writing reflex. We send that to the cerebellum. The cerebellum is the area, the second largest area of our brain. It's the base of our brain underneath the cerebral hemispheres. And the cerebellum deals with equilibrium, it deals with, muscle memory, and so, we know left and right and up and down, and we know memory and how to react. We have learned reflexes get stored in the cerebellum, and this thing like raising our head up to become level with the horizon. So our eyes are level with the horizon. That is information that's sent to the cerebellum because we're dealing with, balance. We want to know which way is up. But something else that proprioception does for us is it allows us to coordinate the movement of our eyes and our hands. And hand-eye coordination, or eye-hand coordination, requires us to be able to track objects in space with our eyes, plot their movement, and then reach out our hand at the appropriate location and catch the object, or at least knock it down. So we have to guide our hands. We have to see the object, plot its motion. So we have to have movement of our eyes, and we have to be able to use the position of our hand in space, so we can place our hand in the right location at the right time with the right force to catch the object. This is eye-hand coordination. And so there's a very large proprioceptive component to this. So, and a lot of eye-hand coordination becomes a reflex. It is, reflexive to respond to objects that are moving at you. You may catch them, you may dodge out of the way, you may knock them down. These are all different things that we encounter. We use a variation of this when we drive. I mean, think about it. You pulled up at an intersection and you're watching the traffic go by, trying to wait for an opening, and you look to the left, you look to the right, and you have to assess how far apart the cars are. Can you get out through the intersection? Can you make your left turn or your right turn? How far away are the cars? When will they get to where you are? You assess that all the time. It is a type of proprioception because you're monitoring your position. You know your position in space, and you're watching them, and you are calculating in your head how rapidly they're coming and whether you can pull out or not. And that's one of those decision-making processes in proprioception that improves as we get older. We have, because of experience in driving. We assess that. And then, of course, once we get, once we're dealing with our elderly patients, then that seems to go straight downhill, because many of our elderly patients then lose that ability. Not all, but some do lose that ability to assess properly. And so they pull out at inappropriate times. So anyway, what's a reflex? It is an involuntary, rapid, predictable response to a stimulus. A reflex will always give you the same response. It is predictable, meaning if you put your hand down on a hot surface, you will yank your hand back every time, barring anything else going on. If you step on a sharp pin, some sort of sharp object, you will yank your foot back. Your eyes will blink when something gets close to the eyeball. That involuntary means we do not control the action. We don't have to stop. Involuntary means we don't stop and think about it. Oh, I put my hand down on something hot. I better pull my hand back. Oh, that hurts, whatever I'm stepping on. It's sharp. It hurts. I should pull my foot off of it. No, it happens much faster than that. It's involuntary and it's predictable. A reflex is always predictable, meaning that the response will always be exactly the same. It will give you the same response every time. Reflexes are spinal reflexes, a spinal response. In other words, the decision to do something is controlled in the spinal cord. It never involves the brain. When you step on something sharp and you yank your foot back, the decision to yank your foot back was made at the level of the spinal cord. It saves time. It's fast. Your brain is made aware of the fact that you've stepped on something sharp or hot or painful or cold and icky and slippery. You're still going to yank your foot back. Your brain is made aware of it, but the brain doesn't make the decision to pull your foot back. Brain is only informed of what happened. The spinal cord makes the decision. It's still the central nervous system. The spinal cord makes the decision to yank your foot or back or pull your arm back or to whatever, to sneeze when you're exposed to an irritant. So reflexes are one of two types. They are either inborn or what we call intrinsic. This is the classic rapid, involuntary, predictable motor response to a stimulus. Posture is a reflex. Standing upright, maintaining your upright position while seated or standing is a reflex. Visceral activities are reflexive. When you put food in your stomach, the stomach will churn. When you put churned food in your small intestine, it will be pushed through there reflexively. You don't have to stop and think about it. It will be absorbed as nutrients and waste product will end up in the large intestine. Those are all visceral activities that are reflexive. We don't have to do anything about that. Our eyeballs, in bright light, the pupils will enlarge. In bright light, the pupils will shrink. In dim light, the pupils will enlarge. We don't have to think about it. Oh, it's bright. I better bring my pupils back in now because it's too bright. No, we don't have to do that. Those are intrinsic reflexes. Now, we can force ourselves through conscious effort to override some of those reflexes. We can force ourselves, we can teach ourselves how to respond differently. We can, we're frequently stimulated by sound and light and motion that we may have to force ourselves to ignore or to become even more sensitive. So that's the intrinsic reflex. Now, the other reflex is something we have a direct impact on. That is a learned reflex. It is acquired. It comes from practice. It comes from repetition, doing something over and over and over again. With repetition, we generally get, when we practice, we get better. The more we practice, the better we get, theoretically. Yeah. Some people just never get better at what they do, but most people will get better with their activities if they practice. Repetitive motion allows us to do the same activity over and over and over again, storing muscle, creating muscle memory, storing the correct output in our muscles so that we can do it quicker and more precisely than we did before. The more we practice, the better we get at it. playing an instrument, playing a sport, driving your car. That you get, the more you drive, the better you get. We probably have all buried the thoughts of the first time we ever drove a vehicle, and how much fun that was being taught, particularly if it was by a family member. However, once we learned to drive, we got better at it. Let's go back even further. Learning to ride a bicycle. The first time we were able to ride a bicycle without hitting the sidewalk, without falling down. When we were able to put together the combination of speed and power and balance to move along on the bicycle and to stay upright, we had learned our reflex. We had learned the reflexes to maintain our balance, to pedal the bicycle so that we had enough speed to keep the centrifugal motion going on the wheels so that we could go forward and not fall over. Didn't know riding a bicycle was so complicated. However, it's also one of those skills that we never lose. We never lose the skill of how to ride a bicycle. And it's interesting, we rarely lose driving skills. Many individuals, when they get older and develop, if they are unfortunate enough to develop a dementia, many people with dementia may lose memory on who people are, or what they had for breakfast, or how to button their shirt correctly, but they can tell you things that they did 40 years ago, and they don't forget how to drive. They can drive very well. They don't know where they're going, but they know how to do it because those skills were laid down for a long time, and they're some of the last skills to lose. So practice and repetition become learned reflexes. Reflexes are very, very fast. Indulge my Star Trek video here. A reflex is very, very fast. We don't have to stop and think about the reflex. We don't do what's happening here. We respond. We respond to all sorts of stimuli. It doesn't have to be pain. It doesn't have to be temperature. We turn our head when we hear a sound. We respond to motion. Our peripheral vision from the edges of our photoreceptors in the eyes. We respond to motion, and we respond very quickly. We call it peripheral vision from the, as we say, in the corner of our eye. We caught a glimpse of something. Well, we respond very well to that. And so these are very, very fast responses. So reflexes are designed to protect us. This is a learned reflex. An individual does not learn to be a professional baseball player or professional softball player without lots and lots of practice. Do you think the person at third base waits until the ball is hit before they decide to run over and block the ball and then automatically throw it to first base? It is a learned reflex to dive to their right as the batter swings, dive to the right, anticipating the ball going down the third baseline, and then automatically throw it to first base. That's a learned reflex, and it takes lots and lots of practice at that level. So now, if we're looking at reflexes, what is a reflex? Well, of course, it's a rapid, predictable response to a stimulus. It's going to give you this. Any reflex will give you the same. Any type of reflex will give you the same response again and again and again. You jerk your hand back, you turn your head, you gag on a vile odor of some sort. They're always going to be the predictable response again and again and again. Now, a reflex operates through a series of 5 steps called the reflex arc. First of all, you have to have a receptor. Got to have a receptor that gets stimulated. But again, the receptor doesn't know what the stimulus is. All the receptor does is generate an action potential. That's all it does. And all action potentials are alike. There is no difference between an action potential from the eyeball or one from the ear or one from the skin on a touch or pressure or pain receptor. They all look alike. But it's where they're coming from and where they're going to get processed that makes a difference. So the receptor is stimulated. It generates an action potential. The sensory neuron that the receptor is attached to sends that action potential to the central nervous system. There, that action potential is processed in the central nervous system, usually, but not always, but usually in the spinal cord itself, because it's faster. It's faster to do it in the spinal cord than it is to send it up to the brain and back down. So we process the information in the central nervous system. Usually in the spinal cord, we are integrating the information. So we have a receptor, a sensory neuron bringing information to the central nervous system. We process the information in the spinal cord, and then we have a motor neuron that sends the signal out from the integration center to the effector organ. We've decided what to do. We put our hand down on something hot, so we've decided we're going to yank our hand back. We see a bright light off to our right in the edge of our vision. We turn our head in that direction, or we detect motion to our left, or we hear a loud noise and we turn our head in the direction of the loud noise. We respond to the stimulus. So the motor neuron is the signal from the integration center to the motor neuron that says, turn your head in the direction of the loud noise, or pull your foot up off the sharp object, or take your hand off of the hot surface. That's what the motor neuron signal is going to say to the effector. Now, the motor neuron, again, is just sending action potentials down to the muscle cell, for example. And the muscle cell will respond by contracting. That's all muscle cells can do, is they can contract. So we want to pull the hand off of the hot surface. The muscle cells are stimulated with the action potentials coming down the motor nerve, and they contract, and we lift the hand up. So we have a receptor, we have a sensory neuron, we have an integration center that's in the spinal cord, we'll just say central nervous system. We have a motor neuron, and we have an effector. These are the parts of the reflex arc. And for those of us that do better visually, we can see that this is a good visual representation of it. There's our stimulus, a sharp object being stuck into the skin, stimulating a pain receptor maybe, or a touch receptor, or both, sending input on this, an action potential going to through the sensory neuron to the spinal cord. We are integrating here in this area. This is called the interneuron area. So we're integrating in the spinal cord. We're sending our output, our decision on the motor nerve going out to a muscle. And the action potential in the motor nerve will tell the muscle to contract and pull the object out of the skin, or pull the hand away from the sharp object, or whatever's causing the problem is to respond reflexively by pulling your hand away from it. And that's what the reflex arc is all about. Now, we have reflexes that are learned. We have reflexes that are intrinsic. They're natural born reflexes. We have learned reflexes. We also classify reflexes as the type of muscle involved. Are they somatic reflexes? Meaning, are they skeletal muscle reflexes? they going to involve any of the skeletal muscles? You know, are they, you know, in our arms and legs, hands, feet, fingers and toes, things like that. The other reflexes are the visceral or autonomic reflexes. That will be the smooth muscle or the cardiac muscle or the glands. These reflexes involve swallowing when we have something in our mouth, closing the airway when we swallow. That's an automatic reflex. Breathing is practically a reflex. You know, if you know, do we shrink our blood vessels to the skin on a cold day so we don't lose body heat through our skin. If we go outside on a cold day, we're going to reduce the blood flow to our skin so we don't lose heat. That's a visceral reflex. So these are going to involve smooth muscle or cardiac muscle or the glands. We sweat when we get hot. That's a visceral reflex. Sweat glands could activate. That's a visceral reflex. Salivary glands in our mouth become activated when we start chewing on something. We release different enzymes, start breaking down our food. That's also a visceral reflex. So we either have somatic reflexes involving skeletal muscle or autonomic reflexes involving smooth muscle, cardiac muscle, or the glands. Now this is a classic reflex test. We've all seen pictures of this, or we've seen demonstrations of this. And if we were in class, I'd have the rubber mallets out and I'd actually give you a chance to whack each other with the mallet. You know, technically, you would be tapping the patellar tendon to see if you could stimulate the quadriceps. See, what's happening here is this is a test to measure the effectiveness of the spinal cord, the health of the spinal cord, because if you stimulate the patellar tendon, you have to send a series of signals to the spinal cord. You have to, because when you stimulate the patellar tendon, you are causing the quadriceps, the four quads on the top of the leg, they are fooled into believing that they have been told to contract, and they will kick their leg out. At the same time, the hamstrings underneath will be inhibited and told not to move. And so I can show you, it's not as easy as it looks. Whenever we do it in class, we find that it works about half the time, and the other half the time, it doesn't. Somebody's afraid to hit somebody in the leg with the mallet. It's not a hammer; it's a rubber mallet. The person that they're tapping is holding their leg too stiff, or they're not hitting the patellar tendon in the right spot. So it happens. This is what should be going on here. Now, what really is happening, this is the patellar reflex. It's a test to measure the activity, to measure the health of the integrating center in the spinal column. So right there is our muscle spindle there. Okay. When we tap the patellar tendon, there's the patellar tendon right there. Okay. We tap the patellar tendon, and the patellar tendon causes by tapping on it, causes the muscles, the quads, to stretch. And the sensory receptor in the muscle spindle says, hey, we're stretching. We're being stretched. We did not have a signal to contract, but we're being stretched because you're tapping on the tendon, and it provides an illusion to the quadriceps that the muscles are stretching. So the muscle spindle will send a signal through the sensory neuron to the integrating center in the gray matter of the spinal cord, And the spinal cord will process that information and send a signal out on the motor neuron. That's number 4 there. And that will activate the quads to contract and kick the leg out. All because we stretched all because we tapped the patellar tendon, the tendon that holds the patella in place there. We tapped that, and it made the sensory receptor, the muscle spindle, think that the muscle was being stretched. And it probably was to some extent, but not very much. So just tapping it makes it believe it's being stretched. That triggers the whole process. Now, the other thing that happens is that causes the hamstrings. We have a second signal going to the hamstrings here saying, relax, don't fight the kick out. Because remember, the quads have not received a signal to contract. They've been led to believe that they're being stretched, but they're not really. And the hamstrings are told, don't do anything. So relax. And so the quads will cause the leg to kick out. There won't be an antagonistic counteraction by the hamstrings. And so we get this. And it's a pretty sophisticated, for as simple as it looks, it's a pretty sophisticated test because there's a whole lot of action that has to take place here. Because we have not just a sensory input and a motor output, but we have a sensory input and 2 different motor outputs. One to stimulate the quads and the other to inhibit the hamstrings. And if someone who knows how to do this test is doing it correctly, and your patient's relaxed, and because your patient's going to be, they may be nervous, they may be agitated, they may be trying too hard here. Your patient, if you're testing them, if everything works right, then their leg's going to kick out. If it doesn't, then that is going to indicate there's something. There might be something going on in the central nervous system. Reflexes are a very simple but non-invasive way to at least get an idea that there might be something not working properly in the central nervous system. So, and that is the end of general senses and reflexes. Let me get out of here. Okay, any questions on any of that? Okay, next week we are going to go into the special senses, and then the following week we are going to dissect virtually a brain and an eyeball. I'll do it here, and you can watch me do it, and we'll see the different parts of the brain and the eyeball. This is what you would be doing if you were in class. So anyway, so you get to watch that and see the structures. And next week we'll talk about the special senses and how they work. And then we'll go through on the, what will that be? The 11th of April, we'll go through and have the brain and eyeball day. And probably next week, I will have to open up the muscle test in lab. So we really do need to get that out of the way now. I'll let it ride till probably next week. We'll see. We'll talk about it then. So, okay, let me get you out of here, and I thank you for your patience, and I'll see you in lecture on Wednesday.